So what do I do?
Well.
Yes. How about we write? How about we write f prime of x equals the limit as delta x approaches 0 of that's the f at x plus delta x, then minus the original function, all over delta x. I like it. You did it in your head, that's fine with me. So we have the limit as delta x approaches 0 of like that? Okay. Plus x plus delta x. Okay. And if you wanted to, like if you had this in your head already, you could have distributed that in your head as well. That would have been fine. So all over delta x. So this is actually, I'm just going to distribute here so I don't have to rewrite it here. 3x squared plus 6x delta x plus 3 delta x squared. And now we have some things that add to be 0. Yes, the 3x squared and the negative 3x squared are gone. Anything else? Yeah, there's a positive x here and a negative x here. Anything else? That's it? Okay. So equals limit as delta x approaches 0 of what? All over delta x. Now what? Factor that delta x out. So this becomes plus 1. Don't forget about that 1 in front of that delta x. Yeah. See, that's the danger about just canceling. Like if I'm here and I'm like, oh yeah, I can cancel here, 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 and here. If you forget that this is actually a 1 delta x, then you can lose that. I think that if you factor out first, you might remember a little bit better that there's a 1 there. There's no saving you. So now I can take the limit. This divides out here. And I can take the limit. I can direct substitute that delta x in. This delta x term goes away. And I'm left with just 6x plus 1, which is f prime of x. So this is the derivative function. And now we're asked to find the derivative at those two ordered pairs. So before I do that, let's take a look at the graph. We have 0, 0. So that looks like I'll probably have a slope of something positive. You could probably guess that maybe it's like around 1 or something. Okay? And then at 1, 4, we're way up here. Something way more positive than the first one, right? Maybe it has a slope of 6 or something. I don't know. So now we'll evaluate this. We plug in what? The x values. So we have f prime at 0 equals 1. F prime at 1 equals 6 times 1 is 6 plus 1 is 7. So those then are your two answers, which represent what? The slope of the tangent line at those two ordered pairs. Yes. Okay. I'm starting, my confidence is improving slightly. Hopefully yours is too. All right, special cases. We've been talking about continuous functions. These are special cases of continuous functions. So the function, I shouldn't have an S there. The function is continuous, but the tangent line is vertical at x equals c. So the way that would happen is if I had a graph that kind of does this. And we do have graphs that do this. They go vertical right there. So the function is actually continuous, but if I try to find the derivative here, I'd be finding basically a vertical line slope. And there is no slope on a vertical line, right? It's undefined. I shouldn't say no slope. It's an undefined slope for a vertical line. So therefore, you can't find the derivative there. The limit as delta x approaches 0 is infinity because of the division by 0 on that vertical line. So therefore, the function is not differentiable at that point. The function is continuous, but it is not differentiable at that point. The second case, the function is broken at x equals c. We've talked about broken functions a little bit in here. If I have something that does, say, something like this, that would be a broken, that's a piecewise function. Or you could have like a greatest integer function going on. There's an infinite number of tangent lines at a break. And the reason for that is what you're doing all along here is you're finding the slope of the tangent line, right? Well, what is the slope of the tangent line at exactly that point? I don't know, because I could put a tangent line that only touches here once, like that. Or I could put a tangent line in that only touches once, like that. Or I could do another one that only touches once, like that. There's an infinite number of tangent lines that I could put in there. So therefore, we can't describe the slope at that break, which means that the function is not differentiable at that break. The third one, the function has a sharp corner at x equals c. Basically, if we take a look at an absolute value function, so the sharp corner would be right here at the vertex of the absolute value function. And the same thing holds true as we just talked about in the other one. We have a point right here that I can draw an infinite number of tangent lines through. So therefore, I can't differentiate there. Everywhere else I can differentiate, but not right at that point. So each one of these three examples is continuous, but it has a special circumstance that doesn't allow us to take the derivative at that particular location. All right, let's get away from basic parabolas and let's move on to more complicated functions and find their derivatives. So we have the derivative of, we want to find the derivative of f of x equals x to the third plus 2x. The process is the same. Let's set this up. What will I write?
Okay, so
f prime of x.
F prime of x equals, okay, of plus x plus delta x, finishing off the first part. Okay, now, the bummer here is that we are going to have to cube this thing, which means we need to remember how to cube something. So off to the side, I'm going to figure that out. All right, so now that we know what the x plus delta x is, it follows Pascal's triangle, the pattern that we just talked about, we will write equals limit delta x approaches 0 of that, which is plus this guy now, 2x plus 2 delta x, minus this guy, so minus x to the third minus 2x. All of that is divided by delta x. That's it?
Yep.
Okay, the x cubed minus x cubed is gone. What else goes away?
2x.
The 2x is gone. Anything else? All right, so let's rewrite this then. Equals limit delta x approaches 0 of, what's left over? 3x squared delta x plus 3x delta x squared plus delta x to the third plus 2 delta x. And that's it, right? Okay. All divided by delta x. So now I'll rewrite this with that factor coming out. Delta x out front, and now I'm left with 3x squared plus 3x delta x plus delta x squared plus 2. All divided by delta x. We can divide out. And then I can also take the limit right now, save myself a little bit of writing. I get, what? 3x squared plus 2. So that is f prime of x. So find the derivative of this function, and I am giving you the graph on the majority of these, so let's take a look at the graph real quick. It is a cubic polynomial, so we do have sort of a cubic looking polynomial on our graph, okay? All of the interesting stuff here is graphed. Like, I'm not just showing you this little bit right here, right? So let's find the derivative, and then let's use the derivative to kind of talk about what's going on the graph. What do I do?
Okay, I'm going to talk.
Somebody else talk.
Yeah.
That table.
Yep.
This table. Let's go.
When you take f times x
Good.
equals the limit and delta x goes to 0, and then you put x plus delta x in the x.
Good. So I'm going to write what?
2 parentheses x plus delta x goes into 2 minus 5 open parentheses x plus delta x plus 1 minus that.
Minus the original. This is the most important part right here. A lot of people will forget. Like, they get so excited about getting through to here, they'll forget the minus f of x part. I'm just telling you what people normally do. So minus 2x to the third minus 5x plus 1. Okay, and then all of that is over delta x. Now what? Pain and suffering ensues because you realize that you're going to deal with this, right? But we already know what it is. What is it?
X cubed.
Can we just write this up here real quick? It is x cubed delta x cubed, right. Okay, so now we know what this is. Let's distribute that 2 in. Okay, so I'm going to write equals limit delta x goes to 0 of plus 2 delta x cubed. My arm hurts. Minus 5x minus 5 delta x plus 1 minus 2x cubed plus 5x. Good. All over delta x. Do we have anything that goes away?
One.
Really? Tons of stuff? The ones do go away. The 2x to the thirds go away. What? 5x. Oh yeah, 5x and 5x go away. Is that it? Okay, factor out the delta x and rewrite it. That's a good idea. Okay, equals limit delta x goes to 0. We know that every term here has a delta x left in it, so we're going to factor that delta x out. And now I'm going to write what? Minus 5. Is that it? Okay. All divided by delta x. And now, very happily, we divide out our delta x's, which means now we can direct substitute. So we get our answer, f prime of x equals minus 5. Boom. Now let's take a, so that's not that bad, right? Okay, now let's take a look at the actual graph. This is the function that tells me what? At any given point on the graph. So if I just pick right here, say, what do you suppose that would be for a slope?
It's almost negative
So, yes, but just looking at the graph, the slope looks pretty steep and positive, right? So if I plug in, let's plug in -2, because we'll get a pretty steep positive slope, right? We should. So if I plug -2 in here, I get 4 times 6 is 24, minus 5. Pretty steep positive slope. What if I plug in 0? What should I get? A pretty negative slope, okay? So I plug 0 in here and I do get a slope of -5. What if I plug in, let's see, +1? So down here, it looks like I'm kind of like this, maybe a slope of around 1 or so, right? So I plug +1 in here and I actually do get 1, exactly 1. That was a coincidence, I didn't plan that. Where have I not talked about on this graph? What do you mean by the curve? Where it turns. So what would the slope be where it turns around? 0, okay? If you look at this graph, does it look like maybe if I plug -1 in there? That's a great idea. That's a great idea.
I saw that coming.
How could I figure out, if I was asked, and I'm not asking you right now really, that's not in this section, but it is coming. How could I figure out where the slope is 0? I mean, I can see it on the graph, but exactly where is the slope 0? What could I do? Put 0 in here, right? Because this is the slope, and I want a slope of 0. So I could go 0 equals 6x squared minus 5. And then you could factor it, or you could just solve for x. In this case, we're going to add 5 to both sides, divide both sides by 6, and you get 5/6 equals x squared. And now I can use the square root property, plus or minus the square root of 5/6, whatever in the world that is. Those are where my slope is going to be 0. And it kind of does look like they match. So that's the idea. Okay? Well, this is where we're going.
Were you saying that it'd be a good idea if we were going to do it, or it'd be a good idea but we're not going to?
This is where we're headed right here. For right now, you only need to worry about this. But down the road, in this chapter, we are going to be doing this a lot. So far, we've only been working with polynomials. This one isn't a polynomial, but you can still do this process. Okay? It's complicated, but you can still do it. So I want to find the derivative of f of x equals 2 over x. To do that, I'm going to write f prime of x equals the limit as delta x approaches 0. Nothing has changed, right? But now I'm plugging in x plus delta x, just like normal. So this is going to become 2 over x plus delta x. Minus f of x, 2 over x, all divided by delta x. Now, if you think back about a month ago, I gave you problems that looked somewhat like this, okay? So there was a reason that I did that. It's because you could now handle something like this. So what do I need to do first? Yeah, we need to simplify the numerator first. We need common denominators in the numerator so that we get one fraction only up top, okay? So what will my common denominator in the numerator be? X plus delta x times x, right? I have a factor here of x plus delta x. I have a factor here of x. So I'm going to match, and I'm going to match. Making fancy ones so that I'm not changing anything. Everybody agree with that? Okay. So now I'll rewrite what I have. This is the limit as delta x approaches 0 of, in the numerator of the numerator, 2x minus 2x minus 2 delta x. Nice. Divided by, I'm not distributing that. Leave the factors alone. X parentheses x plus delta x. All divided by delta x. Now I have a composite fraction here, stack fraction. This is really like delta x over 1. Leave it, change it, flip it. So where does this delta x wind up then? In the denominator. So let me rewrite that just so we see it. Limit as delta x approaches 0 of, the numerator is negative 2 delta x. I'm simplifying this. divided by that x parentheses x plus delta x times the delta x tacked onto the end from this guy. And there we go. We can divide out the delta x. So we now have equals, I'm just going to write this down so we see it, limit as delta x approaches 0 of negative 2 up top divided by x times x plus delta x. Can I now direct substitute? Yes, I can. Usually when you divide out, you can direct substitute. And this is the case here. So I can substitute 0 in for that delta x, and what do I get? Negative 2 on the top over x squared. And that's the answer. Now, this tells me that I have division by 0 when x is 0, right? Kind of like up here, I have division by 0 when x is 0. So what would the slope be if I plugged in 0 right here? It'd be an infinite slope, which tells me that I have a vertical asymptote sitting here, okay? We can't divide by 0, but when we're talking about the slope, we can say I wind up with an infinite slope here, which means something wacky's going on.